Hello, everybody. Can you hear me?
Yes.
Okay, good. All right. So my apologies for being a little late. Unfortunately, when I was going out the door, I had to use the restroom. So nature calls, and unfortunately, it messes up schedule. So I plan to be here early for the last couple lectures. I'll try to be early next time. So any of you who are distant, do any of you have any questions of me? Regarding anything?
The worksheet that you sent out over the weekend, is that something that we're taking in today, or is that just practice for the test?
It's practice, and I gave you the deadline of today because I wanted essentially for you to finish it off and start studying for the exam. So.
Okay, thank you.
Yeah, and you're welcome. If you have any questions, email me a picture of your question. I'll be glad to answer it. So I'll be glad to go over it with you if you want. Just we'll set up a Zoom and do that. Okay?
Okay, so we don't turn that in? We don't turn that paper in?
No, it isn't necessary because I want you to study from it.
Okay, thank you.
And try and find your right answers. And if you are clueless about something, just ask me. I've already helped a few students already over the weekend. So I'll be glad to do it with you too, okay? All right, now let's start. As I said, I want to finish off the last chapter, chapter 8, with some more stuff that is included in it. It's the whole nature of intermolecular bonds that kind of leads into essentially leads into the next chapter, which is about gases. And basically, it's related to the polar aspect of these things, polar, covalent, and such like that. And I think this is a good place to start with this. Okay, now I'll share the screen with everybody. Okay, can everybody see the screen there? Can everybody see the slide?
Yes, sir.
Okay, now remember the whole thing about polarity is you got regions that are positive and negative depending on where the dipole is. Okay, so for example, this part here is negative. This is negative because of these electron pairs. This area is positive because of the electron pairs. And so essentially those can interact with each other. And when they interact with each other, there's what are called intermolecular bonds between them. So it's called intermolecular bonds. Now, why would there be, based on what we already discussed regarding covalent and ionic bonds, why would there be natural for intermolecular bonds to exist? Why is it sort of normal with these kind of molecules? Because what regions do you have? You have positive and negative regions. Now, those positive and negative regions will interact with one another. What's going to interact with the negative region? The positive. What's going to interact with the positive region? The negative. And essentially, when you got a whole lot of molecules together in a cup of water, basically it will be a liquid. Okay? What happens if you heat it up? And this addresses what we're going to talk about much more next semester, but unfortunately, the way this book is laid out, it covers it at the end. What's the nature of the thing that will cause it to, those molecules to move around faster? You heat them up, you provide energy to them, okay? And eventually, if you provide enough heat to it, it will boil and become a vapor, okay? So that's the nature of a gas, okay? It'll go from a liquid to a gas. Now essentially, these relationships between each other have to do with these different things. Now, what do you suppose has a lower boiling point? Something that's polar or non-polar? A lower boiling point. What'll take less energy to kind of interfere with those intermolecular bonds? Something that's non-polar or polar? Non-polar, because there's no interactions between the different bonds there, okay? And they have certain labels associated with these. These are called intermolecular forces. Yes. And
So,
this will be on the test. My apologies for that screen. Yes.
so if all the arrows are facing the same way, like all the electronegativity arrows, that means it's polar, or that means it's nonpolar?
Well, if they all cancel out, it's nonpolar because it'll be like all positive around it or all negative around it.
Will you go back 2 slides?
Right here, what's the nature of this around everything? Here, this is negative. Here, this is negative. This is negative because all these electron pairs are shoved out from the center. Okay?
So that's nonpolar.
That's nonpolar, correct.
Okay. Would you go back one more slide? And so with the one on the right, would that
That's
be
polar
polar?
because you got
Polar.
negative regions and positive regions. So the intermolecular forces will be higher with polar substances. And there's certain definitions that we'll talk about in a minute. Okay?
But the one on the left would be nonpolar because
The one on the left here is polar also because this has a negative region and this is positive. See, it's because the dipole goes towards the nitrogen and then out towards the electron pair.
but if there's 3 positives, like 3 hydrogen going with the electronegativity going towards the nitrogen and 1 negative,
Well,
how is that?
no, this is the positive region, this is the negative region. And it's just, it kind of moves around and that's a polar system, okay?
Okay.
So there will be intermolecular forces between that for ammonia. That's why you can liquefy ammonia fairly easily by just putting a little pressure on it. Okay, and we'll talk about that in the next chapter. Now, intermolecular forces. In gases, the particles feel very little attraction to one another and free to move around. In liquids, they are held together by attractive forces. Okay, and those attractive forces would be like these. Between the water molecules. Here, you get the hydrogen over here, and then another water molecule over here. These will interact. These kind of bonds between them, that is called a hydrogen bond. Bonding. And it's specific related to water and water solutions, hydrogen bonding, the concept of hydrogen bonding. And it's not the same thing as hydrogen bonds with a hydrogen molecule or within one water molecule. And then a solid, you got everything together. Now the types of intermolecular forces, attractions between molecules, these are electrical in origin from the positive to negative. So positive will attract negative. So they will get attracted to one another, okay? The main kinds are ion dipole forces. What's an example of that? Well, that would be like sodium and a water molecule. How would the sodium ion and the water molecule interact? How does the sodium ion interact with the water molecule? Well, you have this plus region here and this negative region there. Those will interact. So essentially you get a whole lot of water molecules all around the sodium ion. That's one reason sodium salts dissolve. Okay? Those are called ion dipole forces. The van der Waals forces, dipole-dipole forces would include essentially where you have like HCl. Now, which side is going to be the negative part? Which side is going to be the negative part? The chlorine, okay? The positive part is over here. So these will interact together if to form the hydrogen chloride liquid. Okay, so essentially these will interact with another one next to it and essentially with this. And essentially you got those dipole-dipole interactions occurring between both. Yes.
The sodium and H2O, but H2O already filled up the octet. So.
Right. These electron pairs on the oxygen will interact with the thing and orient around the sodium ion. And we'll talk about that more next semester when we talk about solutions, okay, and solubilities. But it was addressed a little bit earlier in the precipitation part of chapter 4. Okay, so you could refer back to that if you like. But basically, it's keep it relatively simple at this point. Okay. Now the London dispersion forces are where you got interaction between. So say for example, if you got bromine interacting with another bromine, this is a liquid normally at room temperature. Why? Well, because even though the whole thing is negative, essentially it goes back and forth. So it'll go back and forth to positive, negative, and then negative, positive, because those electrons will rotate around the whole thing. And basically they get different regions associated with each. And so essentially the negative region of this will interact, the negative region will interact with the positive region there. And basically they go back and forth. And that's called London dispersion forces. And that's why bromine is a liquid. And what's the nature of chlorine? Anybody know what chlorine is? That's a gas. So the London dispersion forces are less. Why look on the periodic table? Why would bromine have bigger London dispersion forces? Where is it on the periodic table compared to chlorine? Below it. So it's a much higher molecular weight. It's a bigger molecule. So the bigger molecules, you'll get those electrons move around a little more. And so you get kind of oriented positive and negative things that kind of keep it together. And iodine, of course, is a solid at room temperature, okay, as is astatine. And lastly, hydrogen bonds is the next one, and that's the interaction between oxygen and thing in the water. So essentially, it will expand on freezing. So essentially, these are the interactions there for hydrogen there as well. London dispersion forces. This is a better example of the London dispersion forces. See what I mean regarding that with bromine? It's symmetrical, so it's not polar, but at a given instant, the electrons will flow around and you'll get kind of oriented positive negatives, and that's why it's a liquid at room temperature, is because of these interactions that hold it together. And also why iodine is a solid, because of these London dispersion forces. Temporary dipoles. The key thing is temporary. And these are the numbers associated with these. And if you notice the boiling point of these, chlorine, the boiling point is below 0 Celsius, whereas bromine, the boiling point is 331, which is about 60 degrees Celsius. Yes. Sure. And then London dispersion forces with these, if you got more stretchy ones, they'll have higher boiling points, part of because of the interactions between all the things together, and you'll get positive negative regions, then a smaller molecule there. And as well as what you get is the concept of entanglement, because these long chains will interact with other long chains fairly easily, whereas a ball won't. Yeah. Well, you don't need to memorize the numbers. Just look at the trend. Yeah. And you can see with the iodine here, the melting point is 386, so it's a solid. And that's because of London dispersion forces. Now, dipole forces, these are examples here with dipoles interacting, and essentially they repel each other when they orient with like charges together. So essentially you'll get attraction when they're all lined up like this on the left. This, what? There? Okay, now hydrogen bonding here. This is an example of what I showed you earlier on my previous slide. Yes. It'll be available for you. You can pull it up on the PowerPoint. I just need to move quicker in this thing.
Dr. Douglas, do we need
Yes.
to know the trends of like the dipole moment increase and the intermolecular forces increase?
Well, just yeah. As the molecular weight gets higher, what's going to happen with the London dispersion forces? Brandon? As the molecular weight gets higher, what's going to happen to the London dispersion forces or dipole forces? What's going to happen to them as the molecular weight gets higher? It'll go up, okay? That's the trend. It's a very logical progression here. It's like God designed things very well.
But do we need to know the specific numbers?
No. Well, it may be helpful to know them. Well, you will know them if you're working some problems. I would recommend you do some problems just to illustrate the concept to yourself so you can see that the difference is there. So
Can you show us how to do one again?
how to do one what?
Like one of the problems, like use one of these and like just work it out, how we would work it out.
Well, we don't really have any formulas here. This part really doesn't involve formulas. I'm just saying if you do have them, whatever else in your book, you can do it. And you're welcome to ask me, and I can open the book and show you how to do it. But right now on this slide, I don't have a problem set up, and I don't memorize them either myself. So my apologies. This is not my area of chemistry. The thing, this is more physical chemistry and even analytical. So because it's the numbers are generated by analytical instruments. Hydrogen bonding essentially is like this. The hydrogen bonding is greater with water. This is greater, and this is less. Okay, so what do you suppose has a higher boiling point? Water, yeah, okay, because the intermolecular forces are higher with it. And this is how it interacts with liquid water here with all the oxygens interacting together.
So in a hydrogen bond, water will always have the highest boiling point?
Yeah, when you're comparing it to ammonia.
When you what? Compare to what?
Ammonia. That's ammonia. Here, this
But
is
will
ammonia.
it always have a higher?
Well, it does because the hydrogen bonding is higher, so that'll make the boiling point higher. And it's the nature of the more energy you get for water, it'll eventually turn into steam and evaporate. That's evaporated water.
But how can you tell if the hydrogen bond is greater?
By experimentally, they did it experimentally by comparing water with ammonia. Notice the similarities between water and ammonia. You got this electron pair in ammonia, and you've got 2 electron pairs there for the oxygen. So the hydrogen bonding is going to be a little higher with that because you got 2 electron pairs versus 1. But they can both be gases. But the thing is, ammonia will if you pressurize it, is easy to liquefy also. That's what's in a lot of refrigerators, industrial refrigerators particularly. Now, hydrogen bonding between chains here, there's a whole lot of different examples here of hydrogen bonding. And then intermolecular forces and ion dipole interactions. And this is where you've got a sodium. This is like a sodium ion, This would be like a chloride ion interacting with these. And that's the ion dipole forces interacting. And then this chart is particularly useful to just get a feel for it. The strength here, this is as you go down, it gets stronger, okay? And that's the nature of that system. That's the intermolecular forces thing there. Okay, now molecular orbital theory of the hydrogen molecule, that with different examples of these, there's bonding and anti-bonding orbital, but I don't have enough time to do that. So for those of you who are any chem majors here, I recommend you read that section of the book and just things, but basically that's not going to be on the exam. Yes?
I was going to say, is it on?
No. It's interesting, but I don't have enough time to cover it because I got to do the gas things today too. Yes. No, what I just showed you is on the test. Everything about the intermolecular forces is. Okay, this isn't. No, okay. So basically that's not going to be on the test. So just concentrate on other things. It's more related to the mathematics involved. But you're welcome to read ahead just for your own things. In a normal semester, I usually have enough time to cover it, at least enough. Yes?
So on what you just taught us, like what was the example question you asked? Like how would you ask?
Well, what are the intermolecular forces for water? Or what are the intermolecular forces to bromine to make it a gas? And that's why it's related to the next chapter, which is gases. So it fits very well in there, okay? Okay, so that ends that slideshow. So basically, that essentially ends chapter 8 too. And so now I'll move on to chapter 10. Okay, so let me pull up the next chapter. Okay, now this, what I just did is a good transition into the gas part, and you'll understand the connection with the gases when we start. So let's.
So this is chapter 10, and this is chapter 5.
It's chapter 5 in Chang. It's chapter 10 in our book.
Okay.
These are just better slides. Okay, now here the nature of this, and I got some questions for you. Let me pull it, share the screen with the other group. Okay, when you have gases, certain examples of gases would be like hydrogen, and then chlorine, and then fluorine here. Now, which of these do you think is going to have the lowest boiling point of all these gases? These are naturally occurring gases in the things. What do you think is going to have the lowest boiling point? Why? Yes, okay, but also because of the fact that you've got the interactions between both. It's nonpolar. The London dispersion forces are very low, okay, because you only have 2 electrons shared between it, and the molecular weight is very small, okay. So there's all sorts of factors. Of the fluorine and chlorine, what's going to have the lowest boiling point? The fluorine, yes. Why? Yes, and it's lower in molecular weight. So basically the interactions will be less, and there's less electrons to flow around it, to be moved around. Yes.
We couldn't really hear the answer. So which one is the highest boiling point?
Well, you tell me, Brandon, which is the highest boiling point, fluorine or chlorine, based on what I was talking about earlier today with the forces?
Would it be hydrogen?
Well, that would be the lowest boiling point because this is positive all around, it's the smallest, right?
Isn't that what we were asking?
Yeah, what has the lowest boiling point? Yeah, okay, that's hydrogen, right? Okay. So what of the fluorine and chlorine, what's going to have the lowest boiling point?
Chlorine?
No, the fluorine, because the fluorine is smaller and it's more electronegative, and so basically those electrons are not as easy to flow for the London dispersion forces, etc. So that relates to this next thing about all the gases here. Okay, fluorine, chlorine, and remember these are gases. This is a liquid and this is a solid. Okay, so essentially these are the nature of these related to each of them. Okay, so basically these are elements that exist as gases as you go across the periodic table. Now, why would all the noble gases, based on the intermolecular forces, why do you suppose all of them would be gases? Why is radon and xenon gases? Because the intermolecular forces between them, between atomics, essentially it's all negative around it because of all those electron pairs, 8 electron pairs, and essentially the only difference is radon and xenon essentially is a bigger atom. And here are some samples that are known as gases there. Physical characteristics of gases. Gases assume the volume and the shape of the containers. If you pour a gas into this cup, what's going to happen to the gas? It'll take the shape of it and then eventually come out. Like I could pour CO2 into this and it would fill up the cup because CO2 is heavier than air and it will fill it up, okay? But if you put CO2 in this room, eventually all the CO2 molecules all go through the whole room. And a perfect example of that is if someone comes in the door and they just, if one of your classmates came in the door and they just put on perfume, eventually everybody would smell it. Why? Well, yeah, but the gas thing, why would they eventually smell it? Well, the fragrances essentially that come off of it essentially go through the whole room. That's the nature of gases, okay? But it's different than someone spilling some water on the floor and no one on the other side of the room is affected by it, even though some molecules will go across. That's a liquid, okay? So basically, the gases are the most compressible state of matter because the interactions between them is essentially empty space. You can do that for yourself. Just wave your hand back and forth across the thing. You could feel the gas things hit the hairs on the back of your arm when you move your hand back and forth, okay? Or on your skin, okay? It's compressible. You're doing your hand mostly through empty space. That's why it's easy to move your hand across the thing. How about if you try and swim? Is it easier to move your hand in water or in the air? The air, okay? Because it's very compressible. Water isn't as much. Gases will mix evenly and completely when confined to the same container. Gases have a much lower density than liquids and solids. Okay, now the pressure for a gas, okay, the pressure for a gas is force over unit area, and the concept of pressure regarding gases has to do with what is called atmospheric pressure. And how that is measured is you take a thing of mercury, you put a glass tube in it like that, there's a vacuum up here, and essentially the atmosphere pushes down, and the atmosphere is the weight above everything above us, pushing down on it. That's the pressure holding the air around the Earth itself, the atmospheric pressure of gravity holding all the air in our atmosphere. That all has a weight associated with it, pushing down on us. That provides a force to it, Okay, and the unit area would be like pounds per square inch or something like that. That's the classic thing for that. And force is mass times acceleration there. The units of pressure would be the Pascal, newtons per square meter. And it's also in atmospheres. And this is the one you're gonna use the most, is 760 milligrams of mercury, or 760 torr. That's the unit for pressure. And that's the nature of this little, and this is called a barometer. This is the simplest barometer that can be formed, is having mercury in this and then have it like that. It was easily also done years ago with water first before they used mercury. Mercury was easier because it was a much smaller column. 76 centimeters is relatively short compared to inches of water. Yes. Usually 760 torr millimeters of mercury, or atmospheres for the unit.
What does ATM mean?
Atmospheres.
Okay, and then what does the N and the Pascal mean?
Newtons per square meter. And that's discussed in General Physics 1. Newtons and force and such like that. That's part of why, believe it or not, you have to take physics if you're a biology or chemistry major. Okay. Okay, and then column of air pushing down, that's essentially which is the weight above us, and you can feel it yourself. And for example, at night, I use what is called an APAP machine that helps essentially keep my esophagus open, and not my esophagus, my bronchs open, etc., because I have what's called sleep apnea. But basically, I just get a little higher pressure pushed in, kind of like there to enable me to breathe at night and not snore and such like that. So, but the point is, again, if you're to go scuba diving or something, that's what a tank provides, is your own source of air, and basically it is under pressure, so you can breathe under the water. So basically, the pressure has to do with the nature of that. Okay. Now, manometers are used to measure gas pressures, and basically, if you got a gas, you got a thing related to that, and it's related to mercury. And basically, you're talking about a gas inside a little vessel there, and an open tube one there, or a vacuum. Those are different ones. And then apparatus for studying the difference between the pressure volume of gas would be these. And then basically, as the pressure increases, the volume decreases. That is what's called Boyle's law. And basically, Boyle, let's go back. Just a minute. I'm going to open something for a sec here. Okay, I'm going to shift to this to the last 10 minutes to introduce a little bit more so that the laws make sense here. Okay, this is from chapter 12 of Hein, and it's a little bit more easier to understand at this level. And this will serve as a kind of introduction to when we go over the formulas on Wednesday and finish off the chapter. But basically, this is related to what is called the kinetic molecular theory of gases. And these are the things that are covered in there in a much more basic situation here with combined gas laws and such like that. I just like the slides. I use the same slides for general and intro to chemistry because it essentially covers the same material. So I think this will be very useful to you to have this. Just a sec, folks, I'll get you to see it in a minute. Sorry, I'm trying to share the screen with you now. Okay, this is called the kinetic molecular theory of gases. That's kind of what I was kind of addressing earlier in the slides. And so basically what I'm going to do is go through this regularly quickly. KMT is based on the motion of gas particles. Okay, so essentially you got things moving around. Okay. How would you prove that you can move gas particles? Yeah, or you can blow air out of your lungs, okay? That's essentially the motion of gas particles. If you heat them up, what will that do? It'll cause them to move faster, okay? Because they get more energy there, okay? A gas that behaves exactly as outlined by KMT is known as an ideal gas, okay? When no ideal gases are formed in nature, real gases can approximate them under certain temperatures. So there's certain assumptions to KMT. And this is really, really important, and it kind of will serve as a great introduction to finishing off what we need to for this chapter on Wednesday, okay? The principal assumptions. Gas consists of tiny subatomic particles, like we showed with those slides earlier. They could be nitrogen, oxygen, fluorine, chlorine, all the things in red on the periodic table are liquids, are gases, okay? The bromine is a liquid, the iodine is a solid. So bromine on some periodic tables has a different color, as does mercury, okay? So basically gas consists of tiny particles. The distance between the particles is large compared to the size of the particles themselves. That's why it's compressible, because most of what I'm doing back and forth is empty space. So what I'd recommend you do is read chapter 12 of Hein for Wednesday. It will give it more basic thing, and then you can read chapter 10 of our book too, of the book. Just go through it, but that'll explain it a little better with this. Essentially read chapter 12 of Hein that's related to this whole thing. And he goes in, it's an excellent book regarding how he describes this, okay? Gas particles have no attraction for one another. Why would that be the case? They're nonpolar. Yeah, very good. Very good. And if they do have any attraction, all you have to do is provide a little bit of pressure, like for water or for ammonia. Gas particles have no attraction for one another. Gas particles move in straight lines in all directions, colliding frequency with one another and with the walls of the container. That is the nature of pressure. What happens if I push down on this table? What am I doing to it? Applying pressure. If you throw a ball at a wall, a softball at the wall, it bounces off. What have you applied to the wall? Pressure, force from the ball hitting it. Same thing with air molecules going back and forth. They're hitting the walls. They're applying pressure to it. That's why if you blow up a balloon, okay, It fills up and applies pressure and the thing expands. You're just putting air into it when you blow it up. That is essentially the presumption that's occurring. No energy is lost by the collision of the gas particle with another one. They're considered elastic. In practicality, would that be true? Not necessarily. What's more likely to be elastic? A chlorine interacting with another one, or an HCl interacting with another one? What's more likely to be elastic? They're both gases. Yeah, why? Yeah, and what's the nature of the polarity? Non-polar, very good. The other one is polar, so there'll be some interactions to it. But you can liquefy HCl just by applying pressure to it so the intermolecular forces take over. Okay? The average kinetic energy for the particles is the same for all gases at the same temperature, and its value is directly proportional to Kelvin. So basically, essentially, its value is directly related to the Kelvin temperature. Now, all that is saying is that the higher the energy of those molecules, the faster they're moving. That's all. If say for example you've got a cup you've got a closed container, a can, or a cup that you have a closed container with it, and you've got a bunch of BBs inside and you shake it really hard, what's eventually going to happen to the temperature of the cup? It'll go up because of all the collisions occurring. So essentially, as you provide energy to it, it'll get hotter inside. That's the nature of this, and it has to do with the kinetic energy associated with that. And the definition of kinetic energy, this is why this chapter is covered now, because the first chapter of the next semester will be on energy. But the kinetic energy of gases is 1/2 the mass times the velocity squared. And if you increase the temperature, what's going to happen to the velocity? It'll go up, okay? So all gases have the same kinetic energy at the same temperature. As a result, lighter molecules move faster than heavier ones. And that explains why helium will rise. Helium balloons will rise. Okay, and there's a term for that related to this with the mass of a hydrogen molecule is 2, the mass of an oxygen is 32. So what is going to rise higher in air? Hydrogen. It's smaller, okay? So it's harder to keep it in place. So essentially, the volumes between both of them. Now, there's 2 concepts regarding that's important to understand regarding the nature of gases. Diffusion, that's the ability of 2 or more gases to mix spontaneously until they form things. These definitions are best read in context. So yes, I want everybody to please read the PDF you have in this bared thing, okay? And your book goes into this too, but in less depth in chapter 10 than Hein will, okay? So, but they cover both of the materials. So I'm not asking you to read 2 books. I'm just asking you to use some things. Now, if you have diffusion, and the example here is someone, for example, let's say, for example, when I was at summer camp, there was a guy that was walking back to the cabin and he got sprayed by a skunk. What happened when he opened the door and came in? Yes, and everybody smelled it, okay, and laughed, okay, because he got into a skunk, okay? That's a good example of diffusion, okay, or my perfume example or something. Eventually you will smell it, okay? This time of year we got burning smoke from leaf fires. You'll smell it outside. That's diffusion. It's the ability for them to shift, and this is an example there. If you open the stopcock, the fusion would occur. Effusion is the second one, where gas molecules pass through a very small orifice from one at higher pressure to a lower. That's like a leaky balloon. So essentially you have got a leaky balloon here. Okay. And basically it'd be like a balloon with a pin in it. And then Graham's law of effusion, when you have same temperature and pressures, they're inversely proportional to the square roots of their densities or molar masses. And that's why, for example, how many of you have ever gotten a helium balloon and had it in your room and then eventually it sank to the ground? Why? Because the helium escaped through the balloon walls and the air came in to replace it, but it doesn't diffuse as well, so it ends up being like this on the floor, okay? But the helium is essentially gone, been replaced by air that came in to replace it by this whole thing of effusion through the side. So basically it's kind of cool if you understand it in context. And basically the rate of effusion, the Graham's law there, is related to the molar masses between both. And there may be a problem in your book regarding this too. An example problem is the fusion rate of those two directly related to the molar mass.
Will you go back for a second, Dr. Douglas?
Sure. This is the first formula you need to learn for this chapter, Graham's law of effusion, because it's related to the molar masses difference. Okay, now what is the ratio of the rate of a diffusion from these two? Well, you just put it in the formula there. The molar mass of CO2 divided by the molar mass of this, the square root, that's 1.25. And so what does that say? What's gonna effuse better, carbon monoxide or carbon dioxide? Just be logical. I said the same thing with helium. What's going to effuse better? Carbon monoxide, because it's only got one oxygen. It's a smaller molecule. It'll go through the pores of a balloon easier. Yes?
Why do you put the carbon dioxide?
Well, that's just the formula. It's inversely related. It was determined experimentally.
Wait, Dr. Douglas.
Yes.
Why did it go from CO to CO2 and CO2 to CO?
Well, that's because the formula, they determined this experimentally, this relationship. The chemist that discovered it was Dr. Graham, okay? He determined that experimentally. Okay, any questions? All right, so we're done for the day. I ask you to read chapter 10 of our book and read chapter 12 of the other one, and I'll get into the formulas on Wednesday. So have a good day.
Can I get my lab?
Yeah. Yep, I'm going to my office right now too. Okay, we're done, so I'll talk to you all later.